The concept of a social network as the underlying roadmap for the spread of an infectious disease can be very helpful when thinking about vaccination, especially in resource-constrained situations. When vaccine supply is not a limiting factor, as is the case for many childhood diseases and regularly occurring epidemics like influenza, then we don't have to think much about efficacy. Ideally, everybody will get vaccinated and the disease will be under control. However, in some situations, vaccine supply is limited. This can occur for a number of reasons. One of those reasons is logistics. For example, in 2009, when a novel strain of influenza, H1N1, started spreading globally, public health agencies across the world raced to provide vaccination for their people. As you can imagine, producing and distributing a vaccine to 7 billion people is not something you can just do overnight. Another reason can unfortunately be economics. The development of a vaccine can be fairly expensive, and these costs can pose a challenge for developing countries. Thankfully, not-for-profit organizations like the Gavi Alliance, Doctors Without Borders, the WHO and others are trying to reduce this problem. But all in all, limited vaccination supply can remain a severe problem, especially in a pandemic scenario. In situations like these, the question arises, who should get the first doses of the vaccine? This is a very difficult question to answer because it really depends on the perspective from which you look at it. Should you perhaps give it to those groups of people first who would suffer the most from getting the disease? Or should you give it to younger people first because you would save the most years of life? Or should you give it to those people who, if vaccinated, would contribute the most to stopping the disease? These are difficult questions with strong moral and ethical implications. What I want to do here is to look at the question from the perspective of efficacy, and we'll use the social network approach to answer this question. So here's how we could formulate the problem. Given a social network relevant for the transmission of a disease, and given a limited supply of vaccines, which set of nodes should you vaccinate in order to achieve the maximum impact to disease spread reduction? The best way to get to an answer to our question is through an example. Let's imagine this is your social network and you only have 10 doses of a vaccine. Which of these nodes would you vaccinate in order to have a maximum impact on disease reduction? You could, for example, vaccinate these nodes over here, but that doesn't seem like a great idea. This group would now be protected, but the rest of the network is completely susceptible. What you should do instead is vaccinate these nodes here, by which you are effectively splitting up the network into 5 disconnected groups. You should then use the remaining 5 doses to vaccinate these nodes here, with the consequence that now all nodes are disconnected. There isn't a single path from an unvaccinated node to another unvaccinated node, which means that the disease cannot spread anymore. What we have just done is to protect the entire network with a limited number of vaccination doses. But in order to do that, we had to pick the right set of nodes in the network. So what's so special about the nodes that we picked? Well, if you look at the structure of this network again, you'll notice 2 things about these nodes. These nodes here are very central to the network. That's not just because they are positioned in the middle of this network. What makes these nodes central is that they lie on many paths between any pair of nodes, and so by vaccinating these central nodes, you are cutting off a large number of paths along which the disease could spread. These nodes over here are also fairly central, but what's particularly notable about these nodes is that they are highly connected. And vaccinating these nodes is guaranteed to have a high impact because you are immediately cutting off a large number of disease transmission paths. So what all of these nodes have in common is that they have a certain position in the network that makes them important for disease spread and thus important for disease control. And this is why understanding the structure of the social network is so important. Just like you want to know and understand the structure of your road system in order to control traffic flow, you want to understand the structure of your social network in order to control disease flow. In the case of traffic, you want to make sure that things flow smoothly and that there are no traffic jams. In the case of infectious diseases, the goal is the exact opposite. You want to cause traffic jams, so to speak, in order to prevent disease transmission. Real social networks are much more complex than the toy network I've used here to explain the concept. But the central premise remains. If you know the structure, you will be able to prioritize vaccination based on the network position of nodes. I'd like to end by repeating that there are many other factors to take into account when making decisions about whom to vaccinate. And once again, these are complex questions with medical, biological, moral, ethical, and practical considerations that need to be taken into account. But clearly, understanding whom to vaccinate to achieve maximal impact on disease spread reduction can only be beneficial when making these decisions.